Hi everyone. Welcome to lecture 9B, second lecture in this module. This one we're going to talk about digital multiplication, just as another example of some digital computation that you can do, basically derive by hand. Um, and I'm going to start introducing you to the field programmable gate array, which is a chapter. Well, it's like a section, I think, in the textbook that I posted on the little chapter I posted on Canvas. Hopefully you can read through that. But it's fairly short, and the amount of stuff you can do with FPGAs is immense. So we'll be using both the breadboard and the field programmable gate array at the same time in parallel in the next few labs. Okay, so first of all, let's remind ourselves how to do multiplication. Okay, going back to elementary schools again, right? If you want to multiply 25 times 14, right? What you do is you line them up once again with their specific places. This is the the ones place. This is the tens place, right? This is the hundreds place. What you do is you take this number right down here, take 4 multiply by 5, and then take 4 multiply by 2, and you add them together. So you're doing some multiplication, 2 steps of multiplication. Oops. Right? So you're multiplying 4 times 5 and 4 times 2. So 2 multiplication. And then the result of that, you add them together, right? So hopefully you start seeing, okay, what's multiplication in digital electronics, right? Thinking about AND gates, okay? And then add stuff together. Previously, we covered adder circuits, right? So we can actually just connect these outputs to an adder and it will add for you. Okay, so you get 100 here, right? 4 times 25. Okay, then you move on to the next place. The way you deal with the next place is that you basically just put a 0 right away, right? This is shifted over. Okay, and you do 1 times 5 and then 1 times 2, and then you get 25. Okay, right, but then it's shifted over by one place. Okay, and then finally you add these two numbers together, right? So you have another adder down here, right? And then you get 350 as a result. Okay, I'm not going to do 25 times 14 by hand in binary, but let's do, I think I have an example that I did. Yeah, 2 times 3. 2 times 3 is nice. 2 times 3. Okay, hopefully the answer will come out to be 6. Okay, so 2 in binary, so 6, let's just carry it. I think this is 2-bit by times 2-bit. So the maximum value of that is actually going to be 4 bits. So let's just have 4 places for them. Let's see why. Okay, so 0. So that's with the 2. And then 3 is the same thing, but with 2 ones instead. Okay, now we're multiplying instead. Okay, so just like what we did here, right? It's the and, the multiplication. 1 times 0 gives you a 0. 1 times 1 gives you a 1, right? And then the rest of these are zeros. Okay, so that's the first row. That's equivalent to this. Okay, the next time we put a little placer 0 here, right away. In fact, I'm try to do it like a little dash line 0 because it's not something we did from a gate, right? We just placed it there. Okay, so 1 times 0 is 0. 1 times 1 is 1. Okay, 1 times 0 is 0. And then 1 times 0 is 0. So there's just extra bits here that you're not going to use. Okay, and then you add these two numbers together. 0 plus 0 gives you 0. 1 plus 1 gets 1 plus 0 gets 1. 0 plus 1 gets 1. And then you have a place here. Okay, and then just you're not dealing with the fifth bit. This just goes overflow, and it's a wire that doesn't go anywhere. Okay, hopefully this is 6. So 1, 2, 4, right, 8. So yeah, this adds up to 6 in decimal. Okay, so notice what we did in this multiplication is that we did some AND operations, and then we have a bunch of adders. Okay, so I found on the internet this 4-bit by 4-bit multiplication table, right? So just to show how this works with arbitrary numbers and 4 bits, right? So once again, you line up the bits, you have the least significant bits on the right, the next one here, next one there, the most significant bit on the left. Okay, and then the first row result is these two, right? Right, A0, B0, the AND, this dot represents an AND operation. Okay, all these are ANDs, so you're going to have a bunch of AND gates in your multiplier, right, which makes sense. Okay, and then what you do is you add these 4 rows of numbers together. Okay, so that's why, you know, stuff like 64-bit input gates are actually very useful. Okay, sorry, 64-bit adder circuits are actually very useful. So these are going to be adders down here. Okay, so let's draw the binary version of this, but for not 4 bits, for just 2 bits. Okay, let's see what this circuit will look like. Okay, so what you want to do, actually skip, I actually want this down here, right? Let's draw that real quick. It's pretty quick. Okay, so 1 multiply 0, 0, 1, 0, 0, 0, 1, 0. Right, the logic is, oops, 1, 1, not 1, 0. Okay, okay. So you have an AND of this, you have an AND of that, and then the rest are 0. You have an AND. You have a placeholder 0 here, and of that is 0, and of that is 1. Okay, and you add these together. Okay, so that's the logic I want. Okay, so the way I'm going to arrange these things, I'm going to put the A's on top. You know, it's only 2 bits, so I'm going to put A0, B0 here, and then A1, B1 here. Let's see if that works out. Is that how this is arranged? I'm going to double check real quick. Okay, sorry. This is not how it should be arranged. Actually, you put all the A's, basically your first number on the top, so A1 goes here instead, and B0 goes here instead. So the first set of number goes across, the second set of number goes vertical. Okay, and what we're going to do, right, the way this logic works was that, we take the B row, so this is the B row, this is the A row, and these are the columns right up here, right? We took B0 and you did an AND to all the A's, right? So what we're going to do is we're going to draw a bunch of AND gates. We're going to draw them kind of funny. We're going to draw them vertical, if I can do this correctly. So this is an AND gate that's vertical. And you put an AND input here and an AND input here. Because, right, not only do you want B0, we'll do the circle here, right? That not only goes to A0, it also goes to A1. You're doing 2 ANDs. Okay, so you draw another AND gate here. I can draw that without messing it up. Vertical is always a little bit interesting for me to draw. Okay, I'm going to skip over this wire. Okay, and then you go down here. So this is another way to indicate that the wire is not connected to each other. It's very much more clear. But by default, you should say that, oh, if there isn't a solid dot on it, then it's not connected. Okay, so this is not connected. Not right. This is connected. Okay, so that's how you do the first row. Okay, the second row, remember we're going to have to shift things over, right? But we still have to take the input from A0 and A0 and A1 along with it also still. So what I'm going to do is I have these gates slightly shifted. I'm going to try to draw this properly. Okay, 2 more AND gates. Okay, and the input of B1 goes in here, and I still want the input of A0 into that, right? Because you're multiplying, let's do this in blue, right? This B1 is multiplying into A0 and A1. Okay, you have to do both all the time. Okay, so this input here hops over here and goes to another one. Okay, and then A1 also gets multiplied to B1. Okay, whew. Right, So hopefully these gets lined up properly. Right, so that took care of basically making these two rows, right? And now we have to add these rows together. Okay, so in order to do that, you make a bunch of full adders. So zoom in a little bit. Okay, so you take these two inputs and you add them together. Okay, there's no carry in. Well, carry in is always 0. Therefore, that's why actually I think they're usually drawn on top like this. Not red. Erase, and then draw that in red again. Right. Okay. So the input of this gets to be the input of this adder. Okay. And then you have the L0 here. And then you have to carry out to the next adder, which adds, let's see, which adds these two other numbers together. So I'm going to make this a little longer. Okay, there's another adder here. Right. So this is orienting this the wrong way. I'm going to label these so I clear for myself. So this is carry in 0. This is you know, A's. I don't want to use A's again because those are actually here. Okay. So this is input 0, input 1. Let's say they're both J. Okay, I and J0. Okay. And then L0 is the first output. Okay. All right. We're going to check, make sure this works. Okay. So this carry in actually should go to the carry in input of the adder. So I'm going to make this a little shorter here. Okay. So this carry out. So this is the carry of the output. Right, that goes into the carry in 1. Okay. And then you're going to get a little bit complicated here. You're going to hop over these wires. Okay. And then the output of this also goes here to the input. I guess I should be consistent on the hopping. If I'm going to do it once, I have to do it every time. Right? Right? And this gives you the L1 output. Okay? And then the carry out here just kind of gets dumped. Okay? And then the carry out of the second adder, right, gets pushed as L2. Okay? And basically this completes this process here. So I'm going to highlight this. Ooh, that's very purple. Let's undo that. Right. That's what's happening here because you're just adding two rows of numbers together. Okay. And then the next thing, right, let's do that blue. These first two rows of operation where you're doing ANDs of the B rows to all the A's, right? That's what's happening here with these AND gates. Okay. And that's basically how your computer does multiplication. You can see how, you know, there's a lot of wiring, right? So remember each of these adder gates are about 19 wires, right? These AND gates adds another, you know, 5 or 6 wires each. So to basically multiply two 2-bit numbers together, you're talking about something on the order of 50 wires connection. And this is why we are going to move towards a different technique. Instead of building these with logic gates on the breadboard, we're going to talk about something called a field programmable gate array. Okay, so that's the next thing that we're going to talk about on this lecture. Let's see, 14 minutes. Okay, so as I said, instead of connecting 1200 wires together, what we can do, and you can actually physically do this on a breadboard if you wanted to. You can lay out all the wires this way. In fact, I think initially they were like this. You can lay the gates out like this. I'm gonna zoom out a little bit. Can I do that here? Yeah, zoom out a little bit so you can see the whole thing. Maybe not. Zoom out a little bit. Let's do it 10%. Okay. Okay. Where you lay the gates out in this two-dimensional orientation, so which is kind of like bringing this back to the multiplier circuit, right? And you have like XOR gates, AND gate, XOR gate, AND gates, AND gates, XOR gates, AND gate, XOR gates. And what we can do is that lay wires, in an array like this. That's why it's named field programmable gate array, right? These are the gates. This is the array, and we're gonna see the field programmable soon. Okay. And basically, right, so since these wires don't have dots on them, that means they're not connected. But what we can do is we can make these connections so that it represents what we did with multiplication, right? This is, I think we're gonna do this with addition. Hold on, let me just check which one is easiest to map out. Okay, so what we can do here, right? So we have this mesh of wires that are not connected to each other by default. Okay, and what you do is, well, let's just start thinking it through this logically. Right, so we can put our inputs. Remember when we have inputs from our full adder? Let's see. So the inputs goes to both the XOR gates and the AND gates. So what we can do is we put our first, this lowest bits, right? These are the two inputs, right? From the two numbers, the lowest bits first. And then you put that input into the XOR gate. I'm gonna write this up here. And the AND gate. Okay, so the way you would do this is you just connect these two wires together, right? Like that. Okay, and then you have a single input that you can put. Okay, so the XOR gate output for the 0th bit, actually that's the least significant bit output, so you can just directly take that, right? The AND gate, if I remember right, the AND gate goes into the second layer of XOR gates. So let's go there. So we need to find an XOR gate, go up this line until we find an XOR gate. Let's put it here. So that's the right here, a bit. Okay. So if we make this connection, basically what we did is we make the output of this AND gate into the input of the second layer of XOR gate. Okay. So that's pretty neat. So then, and then the second set of XOR gate and AND gates here, right? That's what we're going to use for our second bit, if I can remember right. A1, B1, A1, B1. Remember, we put them both, the inputs are the same between the AND gates and the XOR gates at first, on first layer. Okay, and then this XOR gate does not go to the output. It actually goes through the second XOR gate, right? And it goes to the AND gate. So we need to make this connection. So what happens is that whatever signal goes through here, it goes through here, it goes over here, it goes through here. Okay, you're literally just physically making these wire connections. Okay. See, remember this AND gate? Shouldn't it have a different input also? Sorry, output to the second thing. Let's see. Let's go back to my adder circuit, my full adder, so if you get the logic right. So the AND gate, oh, it just goes to the OR gates. Okay. Did I do that right? Yeah, the AND gate goes to the XOR. Okay, so the XOR gate goes to the second layer. Okay, so I was wrong about that. So let's fix that real quick. All right. So, and the cool thing about this is that, well, just like on the FPGA, we want to change the connection. all you gotta do is erase these connections and start over again. Okay, so this first XOR gate does not go to the output. I think I was thinking about the half adder. So the first time you see an AND gate, I'm going to make that connection, and then I'm also going to make the connection to the XOR. Okay, and the AND gate, right? Yeah, come up here, right? It's actually making a connection to the OR gates. Okay, so what we can do is actually pipe this connection up here, because what we're going to do, we're going to tie this straight to ground. So whatever outputs here gets forwarded to the other side. Okay, so you have this AND gate, you go up here, and then you just pipe this output here, right? And this is actually going to be the C out. Oh, I should have that diagram in front of me. That would be useful. Let's see. Let's go back to the diagram. Now you know the process. Okay. So that's carry out 0. Okay, with an OR. Okay. So this is actually going to be carry out 0. Okay, but it needs the other input to be correct also. So let's map that. Where is this? This is the AND of this, the second AND. Okay. Okay, so we make that connection to this, not big enough. We already used this line, so we can't use this one, so I have to use the second line here. So, okay. And then, what's the input of this AND gate? So it's besides the XOR. So let's see what that is. Yeah. Okay. Oh, it's the carry in. Okay, so we need a carry in wire. So let's make this wire carry in. Okay, and then this just goes straight, no connections required. And that fixes this. Now we know the input here. And I think that carry in also goes to this XOR gate. So this is also carry in 1, or carry in 0 actually. Okay, so I got to make that connection. Okay, so now we can deal with the second bit. I think I made all the connection for the second one. Okay, so the carry out of 1 has to be the carry in of the second one. So I'm going to shift these up. So this is carry in 1, carry in 1. Okay, and then once again, right, these connection is going to have to map to this OR gate output here. Okay, and this will kind of go around, and I'm not going to draw that because that'll just mess up the drawing. So you can have these external connections to the back. Okay, and what we do here, right, similar to what we did with the first full adder, right? We want this output of this XOR gate to make connections. Why is this always bothering me? Make this XOR gate. So you want to go find the first AND, make that connection. Find the first XOR, make that connection also. This might cause a problem, but let's just, for the sake of that, let's just ignore that for now. But you can kind of get the idea where you're making the connections. Okay, that's where you can actually program logic into these gates. That way, right, when you make this connection, it forwards that connection. Instead of making it physically on a wire on your breadboard, you're basically just making this, making, whether or not you, for example, push a little rod down to this array of wires, you can make that connection, not that connection. You can remove the connection or not. And that way, you can program any logical operation into these field programmable gate arrays. Okay, that's how you would do it physically on a gate array breadboard. But these days, what you do is actually you do a field programmable gate array. So the field programmable means that you can program it, meaning you write a little program that tells it what connections to make. Okay, and you can do this in the field. That's why it's called field programmable gate array. In fact, you may have run into this yourself if you ever had like a BIOS update or firmware update. You ever heard of those words? That's what it's actually doing. It's basically literally programming these little grids. So these little greens, each of these greens is like logical block, meaning this, it could be a NAND gate or a NOR gate or adder, a full adder in that little logical block. They can design this however you want. And then by programming it, meaning you change whether or not something is connected or not. So how do you do that? The way you do that in modern day electronics is by basically putting a little voltage. So these are very low voltage transistors that you can program. So if you turn on that transistor, right, remember that basically makes the collector to emitter to be conductive, right? So basically, if you can make this little point here conductive or not, that changes how these cells are connected together, right? If this is not connected, then you don't have a connection there, right? So that means when you have when you put that to that the control of that particular transistor unit for ground, then you don't have a connection. But if you put 0.1 volt to it, I think these are very low voltage transistors, then you turn on that transistor and then now you have current running through it, and then you make that connection. Okay, and essentially that's basically how your central processing unit work. So this is kind of a small FPGA, but FPGAs are actually in your computer, your phone, your router, your cars, like my thermostat. uh, they are in a lot of things, and this is how typically a lot of physics experiment used to collect data. Just so to give you some background, so my first experience with FPGAs are actually on electronics board used by the CMS experiment, so which is a giant experiment that's the size of a large building at the biggest collider in the world even now, where they smash protons together at 14 tera electron volts center mass energy. And if you don't know what that number means, don't worry. It's one of the highest energy things we can put together. Okay. And the way we read out the information, at least on the part of the experiment I'm on, is the silicon strip tracker. Is that basically the fiber optics that comes from the detector runs about a couple hundred meters. That's why we need a fiber optics, because the wire, any copper wires will just not make that, will not have a good signal from that. And what it does is that it goes into these boards, and then you have the inputs here. Oops, red, right? And what it does, it can parse the data, so it can ignore certain things. It can say, oh yeah, this is just the information. You can remove noise. You can do a little bit of low pass filter on it, and then convert this to digital information, meaning if the voltage you see is 56 millivolts, it converts that number to 56, and then you can store that on the computer. So it converts that number to binary, ones and zero, so you can actually store that on the computer. So the output of these boards actually goes to like a computer. Okay, and that gets forwarded to the computer cluster at CERN, and then people can look at what the data looks like. We have about 180 of these boards. Each of them can handle about so what's 256 times 30? About 10,000 bits of information, and then we have 180 these. I just know that it's about 1.5 million channels so I have to handle. So what I did between 2009 and 2012 is that me and postdoc basically have to update these firmware like maybe once a month, because what happened is that as you run the detector, certain channel will break because of either some bad circuiting or some flaw, or that it's just got hit by so much radiation that that channel is just dead. So we have to update these things so that When a channel goes dead, we route around it so it doesn't, the computer is not waiting for, oh, what's happening on channel, 56, we don't know, we're just waiting, right? So a lot of these things needs to get fixed. Okay. Right now, I work on a smaller version of this, much smaller, on this neutrino experiment at Berkeley. So this is similar, but less sophisticated. So let's do blue. Yeah, blue is good here. So this is basically the input. So you can see these bundles of wire. These comes from photo multiplier tubes instead. Basically these are signal coming in, okay, and they go into 136 of these channels, okay, as opposed to 1.5 million, okay, and then 135 of these channels goes into this thing, which is the FPGA that we're going to learn about, okay, and this FPGA basically can route these signals however you want, right? Do some logical things with it. So like the things we're interested in is like, oh, whether or not two of the channels light up, and which two is it online, is it a track, is it a track, meaning a muon, did a muon pass through this point, this point, this point in a straight line, right? You can do some simple logic like that, and then basically sends that information through Ethernet, which is what this cable is, this blue cable, onto the data acquisition computer, which is going to record this for future analysis. Okay, so that's what a lot of this. That's why I work on this and also teach this type of class, because it's very useful for, at least if you're going into experimental physics, or you're going in industry where they use this to program your thermostat, right? Just go a little bit more general. So these FPGAs units are also known as arithmetic logic units, meaning that they can do any arithmetic you want. You can do multiplication, you can do adding, you can do bit shifting, you can do, we're going to do in the pre-lab, how to do the 2's complement, right? How do you negate the number, right? But these arithmetic logical unit, the ALUs, are completely useless, right? Because by default, none of these things are connected together, right? If you send data in to something that has no connections, nothing comes out, because you're not going to see anything. Okay, because none of those connections are actually made. So inside, for example, a CPU, a central processing unit, is actually not just the arithmetic, the FPGA part, but also the control unit. Okay, the control unit basically is the bank of information where, oh, if I want to, a bank of instructions, not information, that tells you, oh, I want to add these two numbers together. Can you give me the map to the to which connection needs to be made in order to add two numbers together, right? Basically, the control unit oversees what connections are made in the ALU, okay? And that way, these are known as instruction sets. And so that's why FPGAs are very reflective of what a central processing unit is, because you're going to see on our board, we have the gate array, and we have a control units that you're going to use to program in which connection actually gets made on the FPGA, okay? The other operations, such as, bit shifting, so these are useful for moving data along, or, adding and multiplying, which we know how to do, or even create temporary storage. These are called registers. It's not the best use of ALUs to store information in there, but you can if you wanted to. And these are sometimes temporarily used. So like constants, probably not pi, but like some sort of weird constants where the computer use all the time. Oh, I need to multiply this number, 3.14, blah, 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 all the time. So might as well store it inside the ALU. You can actually do that if you want, okay? And this kind of goes back to what a central processing unit is. So if you ever want to work for AMD or Intel, every time they, I think this happens about every time they produce a new processor, a lot of times they would update the instruction set. The instruction set are actually very long and complicated now these days, because just of the history of it. It's been going on for like 50 years. Um, but if you ever want to look up the instruction sets for a x86 computer, for example, you can do that. If you use a Google search, Intel instruction sets reference, and you can find that in chapter 2 apparently. Okay, and CPU, these CPUs are good in doing a lot of different tasks. Okay, but there are dedicated processing units, meaning is designed to do a specific task very easily. So remember when I did the example with the adder, right? I purposely put XOR gates and AND gates next to each other, right? That made it so that I only need to make like 4 connection or 5 connection in order to do a full a 1-bit 4 adder, right? You can, but that's not necessarily true. If I put a bunch of NAND gates instead, right? First of all, I have to convert those NAND gates into AND gates, and the AND gates to XOR gates. Then now I have XOR gates and AND gates next to each other, right? That takes more time, more connections, right? So dedicated processing units where they can do specific tasks very well, such as inverting a matrix. If you ever did linear algebra, you'll see that inverting a matrix takes a lot of time. If you're doing it by multiplication and addition, there are actually instruction set that does inverting matrix that requires certain logic gates. Okay, and these are usually placed in graphical processing unit GPUs, and these have hardwired together so that you can actually do these tasks a lot faster compared to a CPU. And this is why for certain tasks, dedicated processing units is a lot faster than the central processing unit, because you don't have to send all that instruction over. But in this class, what we're going to do is we're going to do the general version, which is an FPGA. Specifically, the one we're going to use is going to be from Xilinx, which is actually owned by AMD. It's the Arctic 7 chip, which is this one right here in the middle. Better color, please. Okay, that's this little central chip. Okay, and if I remember right, the programmer is usually next to the USB. Yeah, so this is the control unit, and this is the FPGA. Okay. Okay. And basically, this chip kind of tells this chip what connections to make. And the nice thing about this particular card, which is the BASIS 3 from Diligent, is that it has like little LEDs here. It has little switches, and so if you haven't done so yet, please look at the reference manual for the BASIS 3 board. So that way you're familiar yourself with what its capability is, what the input and outputs are actually like. Don't dig too deep into it, but at least kind of peruse through that manual, and that way you know what this looks like and where the things are and what these little PMOTs are actually. Okay, and then you have buttons on top. Okay, that's all for this lecture. So what I'm going to do next, I'm going to show you guys how to use the thing that programs the control units. There's actually a USB connection here. And you basically tell this programmer, oh, what instruction I need to give to the FPGA in order for it to do certain functionality. So I'll show you how to do something pretty basic at first, and then we'll get more complicated as we move on. All right, thanks. See you in the next lecture.